Today we're going to talk about stoichiometry, calculating percent yield. It's part of our Unit 11, stoichiometry. Suppose I want to make some cupcakes. The box says that I can make 24 cupcakes, and when I go to fill the cups in the molds, I find I only have enough for 22. Why didn't I have enough? Well, there could be a lot of reasons. I could have mixed it incorrectly. I could have some batter stuck to the bowl. Maybe I overfilled the cups and I ran out before I had put enough in. Chemical reactions are the same way. Lots of things can lead to them not giving a perfect amount. We always lose some of the product during our reaction. I'm going to define some terms. The first term is the theoretical yield. That's the perfect amount. That's the amount that we calculate we should be able to make given some amount of the ingredient, some amount of the reactant. So for instance, on my cupcake example, the box says I should make 24 cupcakes. That's my theoretical yield. I'll probably need to calculate that theoretical yield using a known amount of my ingredients, my reactants, and use dimensional analysis or train tracks to do a grams to grams calculation to convert to product. The actual yield is the real amount that I made. It's a measured amount of product obtained in the laboratory experiment or the reaction. If you don't do an actual experiment, then it's something that's going to have to be given to you in the problem statement. An example of that would be the 22 cupcakes in my previous example. The percent yield is the ratio of the actual yield to the theoretical yield for a chemical reaction. It's a measure of the efficiency of the reaction. And as a side note, when I talk about yield, I'm talking about what's made. It's the product that we're talking about. So how do we relate the two yields we learned about, actual and theoretical, to this percent yield? As I mentioned, it's a ratio. So we're going to look at the actual yield right here divided by the theoretical yield, and then we'll multiply that by 100 to turn it into a percent. So using the example I've already given you with the cupcakes, the 22 cupcakes that I actually made, that's my actual yield, divided by the 24 cupcakes that the box said it was going to make, that's our theoretical yield. 22 over 24 times 100 yields about 92% yield. Let's look at this with a real equation. I have here iron plus oxygen yields iron 3 oxide. In this reaction, we're supposed to produce 48.6 grams of iron, or iron 3 oxide. Take a look at this term up here, supposed to produce. So that's our theoretical yield. Now, after the experiment was completed, we weighed our sample. So this is an actual physical thing that we've done, and found it to have a mass of 39.2 grams. So this 39.2 grams right here, this is an actual yield. And we get that because we're talking about doing something in our experiment. Calculate the percent yield of our experiment. We look at the equation for percent yield of the iron 3 oxide. It's the actual yield divided by the theoretical yield times 100. So we can substitute in these two numbers, our actual yield 39.2 divided by 48.6 grams, multiply by 100, and we get 80.7%. Now, what about the units over here? Well, let's look back at the equation here. We've got 39.2 grams. It's actually grams of iron 3 oxide divided by 48.6 grams of iron 3 oxide. So we have grams over grams. So these units cancel. So our answer over here has no units, except our percent sign. Now we do want to make sure that somewhere on this line we indicate what we're talking about. I like to put the iron 3 oxide over on the left-hand side. But you can put it on the right as well. But there are no grams here. This is just percent. In example 2, we're going to look at the purple haze experiment. In that experiment, what we did was we mixed aluminum and iodine in the fume hood, and we got a lot of fire and pretty purple haze that went up the fume hood. In this example, we have a calculated amount of 7.55 grams of aluminum iodide produced, and our percent yield is 67.2. What is the actual amount of aluminum iodide produced? Well, this number right here, notice it says it's calculated. So that's going to be a theoretical yield. Our equation is percent yield is equal to actual divided by theoretical. This number is going to go on the bottom, and we already have a percent yield that's right up here in our equation. So we're calculating this guy, which is right in the middle of the equation. What we need to do is rearrange this and solve for actual yield on the left-hand side of the equation. If we do that, we end up with the actual yield being equal to the percent yield times the theoretical yield divided by 100. So now we can substitute in these numbers. 67.2% times 7.55 grams divided by 100, and we get 5.07 grams of aluminum iodide. Notice that grams here doesn't have any other units to cancel with it, so this answer does have units because it's one of our yields. Our percent yield and our theoretical yield both are in grams. It's only the percent yield in percent that does not have units. In this example, we have this equation: carbon monoxide plus hydrogen yields methanol. The problem statement says methanol can be produced through the reaction of carbon monoxide and hydrogen in the presence of a catalyst. If 75 grams of carbon monoxide reacts to produce 68.4 grams of methanol, what is the percent yield of the methanol? Take a look at this number right here, 68.4 grams of methanol. This number, if we notice it says reacts to produce. So this is an amount of a real product, so this must be an actual yield. But what about this guy over here in red? 75 grams of carbon monoxide. Well, the units over here are grams of methanol. Carbon monoxide does not appear to be a product. As a matter of fact, this is a reactant. So it's not a yield. It's not the theoretical yield. So we have an actual yield here, but we don't have a theoretical yield or a percent yield. So how can we calculate the percent yield if we're missing one of the two things that we need? Well, the way we're going to do that is we're going to calculate the theoretical yield. So here's our equation again. Carbon monoxide and hydrogen in the presence of a catalyst produces methanol, CH3OH. We got our train track set up down here, and remember that when we're converting from grams to grams, it's always going to be the same. What we're trying to solve for is percent yield. We have the actual yield, but we don't have the theoretical. All we've got is our 75 grams of one of the reactants. So we'll take the 75 grams of a reactant and plug it into our train track down here. 75 grams of carbon monoxide. We need to convert that to moles. So to do that, we're going to divide it by the molar mass of carbon monoxide. Then we're going to put in our mole ratio of methanol to carbon monoxide. It's 1:1. And now we'll be able to cancel our moles of carbon monoxide. That leaves us with moles of methanol. And we just need to figure out how much a mole of methanol weighs. We'll plug in the molar mass of methanol up here, and that'll get rid of our moles. Now our answer is in grams of methanol. And remember that this is always the same. We start with a given amount of a reactant, divide by the molar mass of that given, multiply by the mole ratio, which we get from the balanced chemical equation above. There's a 1 methanol here divided by 1 carbon monoxide here. But if the coefficients were anything else, if for instance we were looking at hydrogen, we'd have a 2 there. But we plug in our coefficients for our mole ratio here, and then we multiply by the molar mass of the product. It's always going to be in that same order. When we do the math, our answer is 85.8 grams of methanol. So this number is the theoretical yield that we need to plug in up here in this equation in order to get our percent yield. Let's do that. 68.4 grams of methanol divided by the theoretical amount that we just calculated, multiply it by 100, and we end up with 79.7% methanol, or the percent yield of methanol is 79.7%. Notice there are no grams here or anything. In this reaction, we've got NaBH4 plus BF3 forms NaBF4 plus B2H6 diboron hexahydride. We start with 18.9 grams of this. Now this right here is obviously a reactant, not a product. Over here we isolate 7.5 grams of diboron hexahydride. This word isolate means we extracted, we separated. It's a lab kind of word. So it implies we've done an experiment and we've gotten this out. So that's an actual yield right there. But we need the theoretical yield. So the theoretical yield we're going to calculate from our known amount of one of our reactants. We take this and we plug that into our given. Remember, we're going to follow exactly the same procedure. We need to divide by the molar mass of our given in order to convert to moles of given. Now we need the mole ratio, and we're looking at this product, so we're going to have 2 moles of this on top, and we're going to have 3 moles of our reactant on the bottom. So now we're completely done with our reactant because these two are going to cancel out. We'll plug in the molar mass of our product divided by 1 mole, and now the moles here will cancel. We do all the math. 18.9 divided by 37.834 times 2 divided by 3 and times 27.682 divided by 1 if you really feel like it. And our answer is 9.22 grams of diboron hexahydride. This here is our theoretical yield. We were given our actual yield, 7.50 grams. So now we can do our math. 7.50 grams divided by 9.22 grams times 100, and we end up with 81.3%. If you're interested in another practice problem, here I have 2 aluminum and 3 copper 2 chlorides yields 3 coppers and 2 aluminum chlorides. In this example, a reaction was found to have a percent yield of 83.5%. The actual yield was 7.42%. How much copper 2 chloride was used to start the reaction? So this is more complicated. We're going to work backwards on this one from a percent yield back to an original amount of copper 2 chloride used as a reactant. First, we need to determine what the theoretical yield of our reaction really was. If we rearrange this equation and solve for theoretical yield, we end up with 8.89 grams of aluminum chloride produced. So we can work backwards, and if we know this, we can do a grams to grams to calculate the amount of copper 2 chloride that we started with. So we'll start with our 8.89 grams of aluminum chloride theoretical yield and divide by its molar mass in order to get moles. We want to calculate the 3 moles of copper 2 chloride for every 2 moles of aluminum chloride that we ended up with. So we'll put the 3 over the 2. And lastly, after those moles cancel, we need to plug in our molar mass of copper 2 chloride. So we plug that in there and moles cancel and we end up with grams. The answer is 13.4 grams of copper 2 chloride that we started with. Here's another practice problem. We have nitrogen and hydrogen yield ammonia. If we start with 6.75 grams of hydrogen and they react with excess nitrogen, that just means we have enough, we're not going to run out, and we produce 31.9 grams of ammonia, that's NH3, what is the percent yield? So we've got uh, a an actual yield here, and we have one of the reactants here, but no theoretical yield. So we have our 31.9 grams of ammonia, which is our actual yield. We don't know our theoretical yield, so we can't get this ratio to get our percent yield. But we do have 6.75 grams of one of our reactants, hydrogen. So let's use that to calculate our theoretical yield of ammonia. So we'll plug in our 6.75 grams over here as a given. We divide by its molar mass in order to get the number of moles of hydrogen that we're starting with. Our ratio of ammonia to hydrogen is we produce 2 moles of ammonia for every 3 moles of hydrogen that we consume. And now we multiply by the molar mass of the ammonia in order to get the grams of ammonia that 6.75 grams of hydrogen would theoretically produce. When we do that, we get 38.0 grams of ammonia. This is our theoretical yield, which we can now use on the denominator up here to get the ratio of actual to theoretical. So now 31.9 over 38, we multiply that by 100 in order to convert to a percent. And we get 83.9% conversion to ammonia.